Okay, we're back again for Advent of Code 2022. Today is day 11. So yesterday's problem, to recap, was our first glimpse of the virtual machine kind of assembly-esque theme of the month. So of course, because this is very likely to come back in the future, I went and cleaned up an implementation of that to use in future parts, but Eric is generally very good at spacing out these sorts of problems, even on the year where it was all over the place, where like there were 10 questions using it. It was every other day and never 2 days in a row. So I have it at the ready, but it's extremely unlikely that today's problem will be related to that. We'll see what it is though. It is Saturday, meaning a weekend, so the question might be a little involved. We're gonna just try to code efficiently, read efficiently, and think efficiently as well. Fun parsing problem. So when a monkey feels not generic, it goes in the end of the monkey's list. Okay. So this one inspects the first single one. It inspects and throws all the items. So the worry level becomes this, it's bored, worried. It gets times by 19, it's bored, level's divided. Why does it get divided? That's what happens. Oh, I see. But before, after each monkey inspects before it tests the worry level, you're released of the host. Okay. gets equals items A, and then we do the test. So if items like 0, then we divide it. And then if it's divisible by 23, so it's div. Then we do the true operation, and we throw it to the end of the list, I guess, probably. Monkeys of true of, and the list of items is the first thing. This is gonna be when a monkey does an item, goes into the list. If monkey's holding no item to the start of its turn ends. I wonder if this simulation is correct. Probably should do something like this. I make it into a tuple? After one round. Okay. Does it always get bored? Where level is 500, it's not divisible by 23, so it gets thrown to monkey 3. Oh, it inspects all the items it owns. I see. This is closer, but I think there's some divisions that aren't happening somewhere. Oh, there's some multiplications. Okay, that looks right. Chasing all the monkeys, you have to focus on the two most active monkeys. Not the total. most active. Huh? Hello? What is going on? No, I was about to solve the question. What is happening with my WSL? What the heck? Okay, well, that's kind of frustrating. What do we do here? What even is this? I literally don't know how to fix this. Would I have leaderboarded? Yeah. Oh, hey. Okay, we're back. The stream is working again. I literally had the solution, which is kind of frustrating. We're here. So we were at counts, dot values, and then we wanted to sum them or something like that, right? We multiply them. Is like a minus 1 times a minus 2, like that. Is this the number? Yeah, so this is the number for us. Great. Okay, what's part 2? 10,000. Oh, it's the number theory problem. Wait, this is not it? Why did that execute so quickly on my sample? I feel like that's suspicious. I mean, I'll try it. Okay. Okay, do we still have a chance? Nah, the leaderboard filled up. Wow. Well, we could have scored points on part 1. It's kind of frustrating. I guess it's like... we have to inspect the monkeys and figure out like what the pattern is of how they are doing things. So we'll try it out ourselves a little bit. Now we can take a bit more chill since we know we didn't hit the leaderboard. But I wonder what that WSL problem was. That's so strange. So it's probably cyclic, right? The number of times every monkey inspects something each round is probably something cycle-based about it. Or why does this end up going so slowly? Because shouldn't it be pretty fast? I mean, you're just passing the items back and forth. I'm trying to think about why it's actually hanging. Oh, it doesn't cause the worry level to be divided by 3, so it gets really big. So So the numbers are gonna get really big, so we just have to think about what that actually means. We can take a look at the input. So there's 7 monkeys. Oh, is this... So all of the divisibility tests are prime numbers, so that's something interesting. Is it the number theory, Chinese remainder theorem problem? I'm trying to think how that would work though. For every item we have, we do this operation, but sometimes it's multiplication and sometimes it's an addition. So I'm trying to think of what actually happens. And also, why can't we just simulate it? Because this seems pretty I guess the numbers get really big, but I think we can just mod by a big, like, the divisibility is this, so every time we do something like this, we can just mod. So we don't do this anymore. Mod by mod. Because now everything should stay true. But the real question is, what's with the slowdown? Oh, is this just the answer? Oh, okay. Cool, well, this would have been leaderboard points today. It's kind of frustrating. Because when everything crashed and I went to check the leaderboard for today, only 74 spots were taken here, 11 minutes, and then I fumbled a lot of time trying to debug this and I had to reboot the computer. But yeah, I guess no need for a break today because we're already back to live and we can just go over the problem. So let's flip this over here, let's mute the audio and go through the problem. So let's, we don't need this stuff, we don't need this stuff. So this was an interesting problem, I guess. We have a bunch of monkeys, and they take turns doing this thing. So what exactly happens? We start with the first monkey, monkey 0. I won't really go through the whole work of figuring out how to parse stuff. It's just a lot of ugly looking at every line and extracting the useful information, I think. I don't think that's the interesting part of the problem. So what the logic is we look at the first item in our list, then we're going to do an operation on it. So we're going to take this item and, for example, monkey 0 will times the value by 19. That becomes the new value of the item. Then for part 1, we divide that value by 3 and round down. So this makes it so that the values aren't just infinitely growing. So we do this operation, we divide by 3, round it down, and then we check, is the new value divisible by some amount? If it is divisible, we'll throw it to a different monkey, and if it isn't, we'll throw it to a different monkey. So this monkey will do it for all the items until it has no items left. Then we move on to the next monkey, and the same thing happens. Then the next monkey, then the next monkey. So this explanation here is just what happens, and by the end of it, I guess when we go through all the monkeys, monkeys 0 and 1 end up with all of the items. And it seems like this just happens for the sample until at the end we end up with, you know, this. And so what part 1 asks is, different monkeys will inspect things a different number of times. As you can see in this problem, monkeys 2 and 3, they didn't really get to do much at all, right? 2 and 3, well, monkey 3 inspected things, I guess, quite a few times, but during the round, threw it back to the other monkey, so they didn't end up with it at the end of the round. Monkey 2 barely got to participate at all, unfortunately. And so part 1 just asks to figure out the monkey business level, which is multiplying the 2 times that the monkey, of the 2 most inspectful monkeys, multiplying how many times they inspected things together. So the problem actually ends up being not too complicated. It's just a lot of implementation and reading what happens, right? So this is parse input, and then here we can just simulate monkeys, right? And so I guess we should do something like, was this at the end of 20 rounds? Okay, yeah. So let's just do this, because part 2 requires us to do it 10,000 times. So for turn in range 10,000, we're going to do this. But if turn is equal to turn number 19, then let's compute what the monkey level is, right? So it's going to be inspections equals the sorted version of the number of counts that we keep track of. Oh, every time we inspect an item, we just increment this counts thing, and we're going to do this. And the monkey business level is going to be, oops, go away. I want reverse is true. It's just going to be inspection 0 times inspections 1, right? So if we grab the sample, boop, 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 and we run that, we get not the correct answer, of course. Let's I think we're doing one too many rounds after 20 rounds, so maybe turn would be, I feel like this is wrong. 605, should it be 20? No. What changed? Oh, why is this here? I don't need this anymore, and I don't need this anymore. Something changed along the way. Oh, of course. We can't do these both at the same time, because in part 1 we had to do this thing where we divide by 3, and in part 2 we don't actually do that thing. So so we divide by 3 so that the numbers don't become ginormous in part 1, but in part 2 we don't. So just assume this would work. I can restructure the code after to, or actually I'll just demonstrate it. So we want to divide by 3 and ignore this. Yeah, so for part 1 we're doing this, right? We get this answer out. That makes sense. But the tricky part in part 2 is that the numbers are no longer divisible by divided by 3, and we need to keep the worry levels manageable. So if we get rid of the piece of code that divides items by 3, and every round we print out like what the items are, we are in for a scary result, because let's see. Oh wait, that won't work. I want to print, let's do the items. So like this is just one of the items, right? This number becomes absolutely massive, and because of that we can't efficiently do this computation like 10,000 times. So we need to figure out a way to figure to still do this mathematical operations here, because each monkey does something different, right? This monkey's timesing by some amount, this monkey's adding by some amount, this monkey is like squaring the worry levels. And so how can we keep these numbers small enough that our computer can actually keep up and not use up? Oh. Wait, is that what happened? No, I was thinking I just overflowed the RAM in like the Docker container, but I crashed before I even tried running that many iterations and it didn't crash it. So I think it was just a weird bug. I have to investigate that more later. But okay, so for part 2, what's the key intuition here? If we look at these numbers, the thing to note is that the tests for determining where the item gets thrown, these are all prime numbers. And if you look in the input here, these are all prime numbers as well. And I guess even if they weren't all prime numbers, you could still do something similar. But the interesting thing to note about that is this means that because all of these monkeys only care about divisibility by these numbers, if you take the product of all the numbers, this becomes like a grand modulus of the entire system. What I mean by that is, let's just take into account these two monkeys and pretend that they were playing this game together and only passing things to each other. We could arbitrarily take any of the item numbers, mod 10, which is 5 times 2, and they would still always have the exact same behavior of who they're throwing to. That's just a property of modular rings, or whatever it's called in number theory. It's all like one modular system, and right? And so that's basically the key intuition to making part 2 actually possible to work. So at the start of the problem, when we're parsing the inputs, we look to see what number are they trying to divide by. And I track this under the variable mod. So I'm timesing mod by the divisor. So mod becomes, in this instance, 23 times 19 times 13 times 17. And instead of dividing the worry level by 3, I take the modulo by 3, and that just makes sure, I just take the remainder after dividing by this like grand modulus. And this makes it so that the worry levels are never bigger than, I don't know, this number here is probably somewhere in like the 10,000s or 100,000s or something like that. But all of the rest of the mathematical operations stay the same, right? All we're doing here is multiplication, addition, and checking remainders, and these operations are all maintained under integers. They'll be maintained under an integer system modulo this big number as well. So that's just a property of number theory, and that's why this works. And so if we run this instead, we can kind of ignore this part where we print out stuff for part 1. We don't really need that right now. What was this part? Oh, it was just asking us to print out the monkey levels, right? So I guess we can just GCC, we'll do this. And just at the end of 10,000 iterations, we do the same thing. We just run it 10,000 times, right? It's pretty much exactly the same as in part 1. And we get out this big number here, which is this number, and we see that the problem ran basically instantly. Versus if the worry levels kept getting bigger and bigger, like computers are fast, but this number takes up a lot of memory. Trying to do like big num arithmetic is not a fun thing for computers to do. So yeah, that's this problem. I need to figure out why WSL crashed so this doesn't happen again, because it cost me definitely costed me at least 30 points for part 1, and probably noticing the trick pretty early on for part 2. So that's really disappointing actually, but we'll jump back from it. Oh, Robert got first for part 2. That's great. But yeah, we'll be back again for